So you are welcome, Professor Olivier Mathieu.
Okay, so thank you very much. And thank you for the kind invitation. Of course, it's really a pity that this is online. I would really dream to be with you in Kyiv. And I would like to speak today about smooth against versus symbolic dynamics for Anosov manifold and nilmanifold. It is based on an archive preprint which is called Which Nilpotent Groups Are Self-Similar. But before doing this, I would like to ask you to be a bit patient because oops, yeah. You see, this is a famous painting of Magritte, and the title "Ceci n'est pas une pipe" means this is not a pipe. But of course, you see a pipe here. And in my talk, you don't see algebra, but this is really an algebra talk. And we'll see later on that this is really an algebra talk. So first, I need to define three things. I need to define what I mean by smooth dynamics, what I mean by symbolic dynamics, and what I mean by nil manifold. So I start with the smooth dynamics. I start with a compact manifold, M, and I take a diffeomorphism phi from M to M. And you know, manifold, smooth manifold with a diffeomorphism, it is called dynamical system, discrete time dynamical system. So this is dynamics, and it's called Anosov if you have a decomposition of the tangent bundle, which is invariant by the diffeomorphism phi into two pieces, Ts and Tu, and you want that d phi restricted to Ts is contracting and d phi restricted to Tu is dilating, means the inverse is contracting, with respect to some Riemann matrix. So as an example, let me give an example of Anosov diffeomorphism. You take the matrix, which matrix? 2, 1, 1, 1. This is a 2 by 2 matrix of determinant 1. And so A provides a diffeomorphism of R2, but also because the entries are integral, it gives you a diffeomorphism of R2 mod Z2, two-dimensional torus. And you see clearly the two eigenvalues of A are real numbers, zeta and zeta minus 1, with zeta bigger than 1, and of course zeta minus 1 less than 1. And so you see that in the direction of the eigenspace zeta, this is dilating, and in the direction of zeta minus 1, it is contracting. So A is Anosov. Now, a manifold M is called Anosov if M admits an Anosov diffeomorphism. And I would say in my talk that Anosov property is a smooth dynamical system properties. But strictly speaking, experts in the field are looking at diffeomorphisms which are only C1, not smooth. And usually the decomposition of the tangent bundle is simply a continuous decomposition. It's not exactly smooth, but say, I don't want to say too much details, so you can say this is a property of differential geometry, or smooth differential geometry. Now, I would like to explain what I mean by symbolic dynamics. So I start with A, be a finite alphabet. So A, simply a finite set, which is not empty. This is an alphabet. And I choose A be the set of all infinite words. For example, if you choose A to be the alphabet with two letters A and B, a typical element is A, B, A, B, A, blah, blah, blah. This is an element in A omega. Indeed, the words are semi-infinite. They start at some point, but they continue forever. And A omega, sometimes it's called the boundary of a tree, but anyhow, it is a topological space. One way to see it is just a projective finite set AN, but also it can be defined by using some metrics. Simply, you define the distance of two words to be 2 to the minus n whenever the first n letters are identical, but not the next one. So A omega is a metric space. It is called a Cantor set. So what is a self-similar action? I take a group gamma acting on A omega, and we say that this is a self-similar action if for any element gamma in gamma and any letter A, there is some new element gamma A in gamma and some new letter B, such that gamma of AW equal B times gamma A of W for all words W. This is the notion of self-similar action on a tree. And let me remember some definition. An action is called minimal if all orbits are dense. Because here we are on a top space, metric space, which is ultrametric space. Indeed, this is equivalent to say that one orbit is dense. But anyhow, action is called minimal if it's all orbits are dense, and it is called free if all stabilizers are trivial. And the group gamma is called self-similar if gamma admits a faithful and self-similar action on A omega for some A. Similarly, we define what freely self-similar groups or minimally self-similar groups or freely minimally self-similar groups. For the last definition for freely minimally self-similar groups, we require that the self-similar action is both free and minimal. And now let me introduce a conjecture that I'll call conjecture 21, because I found it this year. And it's a conjecture that if the compact manifold M is anosoph, then pi1 of M is freely self-similar. And the theorem 1, sorry, there is a problem.
No, everything is okay.
Okay. If the theorem 1 is the following: if M is if the anosoph manifold M is a nil manifold, then P1 is freely self-similar. Indeed, in the case of nil manifold, the conclusion is slightly stronger than the conjecture because you can add minimally. But in general, for general Anosov manifold, by Anosov I always mean compact manifold, the minimality condition is very unlikely. And I would like to explain why the conjecture is, first I would like to explain what a nil manifold is, because I forgot to give the definition. It simply means that M equal n modulo gamma, where n is a connected and simply connected Lie group, and gamma is a co-compact lattice. So now I would like to explain why the conjecture is very reasonable. Because in 67, Anosov and Smale conjecture that an Anosov manifold is essentially a nil manifold endowed with Anosov diffeomorphism. And exactly this should be the case up to finite cover and up to logical conjugacy. So probably you understand what a finite cover means, something which is nil manifold up to finite cover is called infra nil manifold. I don't understand the terminology, but it's like this. And why do you have topological conjugacy? Okay, this is another topic in algebra. This is because some manifold have more than one differential structure. It means there could be two smooth manifolds which are homeomorphic as a manifold, but they are not homeomorphic as smooth manifold. And the first example, which is well known, is due to Milnor. It is a 5-dimensional sphere, Milnor spheres. And remember that these spheres, topological spheres which are not smooth spheres, have been obtained by Milnor by using 3-dimensional algebraic varieties with isolated singularities. So really, this is algebraic construction. And so there are some nil manifold, something which is topologically conjugated to nil manifold, but which are not nil manifold as smooth manifold. And there are examples by Franks. And basically, it is obtained by connected sum of nil manifold or smooth nil manifold with topological spheres. So it's really so this is why it is up to topological conjugacy, because as a smooth manifold it cannot be correct. So the theorem, sorry. But anyhow, we know that the conjecture of Anosov and Small plus theorem 1 implies conjecture theorem 1. So basically, theorem 1 means that some smooth dynamics of M imply some smooth symbolic dynamics on the fundamental group of M. Now I will introduce the next theorem 2, which is much more easy. the proof is much more easy. But I would like to say that if you have some symbolic dynamics for the fundamental group, then it implies some geometrical property for M, not dynamical property. But so let me remember that a manifold M is called affine if it admits a flat and torsion-free connection. And there was a very famous conjecture or question of Milnor, indeed it is due to Milnor and Schumann, is that any nilmanifold affine? And this conjecture has been proved many, many times. And indeed, it looks like a roller coaster. It has been proved in the 60s, end of 50, and then disproved, and this was at the time of the conjecture, and then prove again, and then disprove again, and so on. But each time, the impression was that people were closer and closer to the solution until beginning of 90, where Benoit, in a very surprising way, shows that this conjecture is wrong. And indeed, there is an 11-dimensional Nil manifold, MB, which is not affine. Indeed, it's a full family of 11-dimensional Nil manifold. And this was a very surprising theorem because everyone believes that the conjecture should be proved at the end. And now I would like to say something about Nil manifold. And it says that if to choose a Nil manifold, and if pi1, if the fundamental group is freely self-similar, then M is affine. So in some sense, Schumann-Milnor conjecture is correct if you add some condition on the fundamental group. But I'm not totally satisfied with this theorem. And so first of all, I would like to say that when I look at Benoit manifold, I can prove that this fundamental group is not self-similar. And so I would like to propose a modified Milnor-Schumann question, is that if pi1 is minimally self-similar, is M affine? Freely self-similar is indeed stronger than minimally self-similar. It's not totally obvious, but it's correct. So this is a way to try to save the Milnor and Schumann conjecture. To be honest, I don't believe too much that the answer should be positive, but the proof of Benoit's theorem is so difficult and so complicated that really I don't think finding a counterexample should be easy. At least with Benoit's methods are not enough. And maybe finding a counterexample of this also brings some new light of counterexample for the Milnor-Schumann conjecture. Now, I would like to explain something about the proof of theorem 1 and theorem 2. And theorem 1 and the proof of theorem 1 and 2 is purely algebraic. And this is why I can give talk in an algebra conference. And indeed, based on a new result about algebraic tori. So it's a purely algebraic. So now I need more hypotheses to explain this theorem, theorem 3 about algebraic tori. And this is really the crucial step and even the most difficult step of the proof. So I need some algebra notions. So I start with an algebraic torus. So it's an algebraic group, which is a torus, which is defined over Q. I denote by X the group of characters of H. I denote by K the splitting field of H. So this is the smallest field, such that when you extend your torus to K, then it is split. So it is split, it is a multiplicative group to the L, and of course L is simply the dimension of H. Another way to define the splitting field, indeed K, K of H, when you apply any character to H, this is in K, for any rational point. And it can be seen that K is precisely the field generated by all these values. So this is another definition of what the splitting field is. But anyhow, splitting field K is another field. It's finite extension of Q. So I can define by O the ring of integers of K, and by P the set of finite places of K. And for a finite place P, let's define by OP and KP, OP and KP, sorry, the pi-adic completion of O and K. And now I fix an integer n, and I set S be the set of places P such that P is dividing n. It means that P is over some prime number dividing n. So S is a finite set. And the theorem 3 says that there is some rational points such that, first of all, chi of H is never an algebraic integer. It means it belongs to K, but not to O, for any non-trivial character of chi of X. Of course, for a trivial character, it's 1. And moreover, chi of H is congruent to 1 modulo n for any chi in X. It remains to explain what this second condition means. This is a technical condition. First condition is the more important condition. And so when you take chi of H, this is an element in K. So you can see it as an element in the completion. And condition 2 means that the image in K pi belongs to 1 plus n o pi. That's the condition. Now, I would like to explain the proof of theorem 3. And I would like to explain it first on some examples. So the first and most obvious example is H equal the multiplicative group of rank 1 and n equal 1. So first, consider the case n equal 1, because the case where n is not equal 1 is really just a slight, is very easy. Does not add difficulties. And so the condition n equal 1 means that the condition 2 is automatically satisfied. So you don't have to care about this, because the set S is empty. So in that case, H, the rational points are just the invertible element in Q. The character group is Z, and if you take an element n, if you take n in Z, the corresponding character is the following. You take H in HQ, and you send it to H to the n. So now you need to find an element H in Q star such that no power of H is an integer. So just choose 2/3. And so you see that 2/3 to the n is never an integer whenever n is different from 1. Because if n is positive, then the denominator contains 3, and if n is negative, the denominator contains 2. So you see, in that case, the theorem is very easy. Now, a slightly more difficult example is a case where H is split, but with rank L, not 1. So in that case, the rational point is Q star to the L. So X character group is Z to the L, and the character corresponding to N1 and L is, so you send H1 HL to H1 N1, H2 N2, HL L. So now if you need to find an element H, what you do, you take L distinct odd prime numbers, P1, PL. You take H equal P1 to the 2, P2 to the 2, PL to the L. So chi of H equal pi1 N1 up to pi L and N 2 to the minus N1 plus NL. And so if chi of H is an integer, you have N1, each Ni should be non-negative. The sum of Ni should be not positive. So it means that all Ni are 0, and it means chi is trivial. So in that case, the proof of theorem 3 follows from the well-known Euclid theorem that there is infinitely many prime numbers. That's been proved around 3 centuries before. Now, to finish the talk, I will explain that when H is not split, one needs a more advanced theorem. And this is which has been proved more recently, 1926, that the set pi contains infinitely many split primes. And let me remember that pi is called split if O divided by pi is simply a product of prime fields. And also we need the fact that the class group is finite. So we need more advanced theorems that Euclid theorem. So this is now the end of my talk. And of course, I do not describe the full proof, but other steps of the proof are really even elementary algebra. So really all the proof of the theorem 1 and 2 are totally algebraic. And this is really, this shows that algebra could be useful to prove theorem outside the field. So now this is the end of my talk. So.
Merci, Professor.